Hey everyone, and welcome to this explainer. Today we're diving into something that is quite literally at the heart of modern electronics, how we take raw electrical power and shape it to our exact will. Our goal for today is to break down exactly how you can take complete control of a DC motor speed using a beautifully elegant real-world circuit. Let's get right into it.
Section 1. The motor speed problem.
So, how do you actually tame a fast motor? Think about your standard 5-volt or 12-volt DC motor. They are absolutely fantastic little devices, but out of the box, they're exceptionally stubborn. If you take that motor and connect it straight to your power supply, you get exactly one result: 100% speed, 100% of the time. It is going to spin as fast and as hard as it possibly can until you yank the power. There's no middle ground, zero finesse. There's just no way to throttle it down to a gentle spin or ramp it up gradually. It's totally all or nothing. And in most real-world applications, whether we're talking about a fan, a robotic arm, or an RC car, all or nothing just isn't going to cut it. We desperately need a way to tell that motor exactly how fast we want it to go.
We basically have two paths before us. The direct connection is your brute force method. Sure, it gives you 100% speed, but absolutely zero control. It's kind of like driving a car where the accelerator pedal is either completely floored or totally off. Terrifying, right? On the flip side, we have the controlled circuit. This is what we're building towards today. This method gives us variable speed and high efficiency, letting us dial in the exact RPM we need. So, to get from that binary state of on or off to having full, smooth control, we're going to ditch the brute force approach entirely and instead look at a highly elegant 4-component electronic solution.
Section 2. Dialing with the potentiometer.
All right, meet our first component, the 10K potentiometer. In our circuit, this variable resistor basically acts as your user interface. Think of it as the brain that's communicating our desired speed. By manually tweaking the electrical resistance, we change the signal. But, and this is a huge but, here's the critical catch, and the exact reason we can't just hook this dial directly up to the motor. A potentiometer is designed for tiny, delicate control signals. It absolutely cannot handle the heavy, demanding electrical current that a physical 5V or 12V DC motor needs to actually spin. If you tried to run that heavy motor current directly through this dial, it would overheat and burn out almost instantly. So it can give the command, but it simply doesn't have the muscle to execute it.
Section 3. The mighty IRFZ44N MOSFETs.
So how do we get that muscle? Well, a MOSFET's job is wonderfully simple. It's used to switch or amplify electronic signals. This component beautifully illustrates a concept I like to call the valve analogy. Imagine a massive, high-pressure water pipe. You obviously wouldn't try to stop that rushing water with your bare hands. Instead, you'd use a heavy-duty industrial valve controlled by a tiny little handle. The IRFZ44N MOSFET is that heavy-duty water valve for electricity. And our delicate 10K potentiometer from earlier? That's the tiny handle. The potentiometer tells the MOSFET what to do, and the MOSFET easily handles that massive, heavy flow of power going to the motor without even breaking a sweat.
To understand how this absolute powerhouse connects to the rest of our system, you really just need to remember one simple number: 3. This specific component relies on an incredibly straightforward 3-pin architecture to work its magic.
Let's break down the function of each of those 3 pins, reading left to right. First up, we have the gate. The gate is exactly what it sounds like. It's the listener. This pin takes that tiny, delicate command signal directly from our potentiometer. Next, skipping to the right side, we have the source. The source connects to the negative side of our power supply. It provides the baseline, the foundation. Finally, right there in the middle, we have the drain. The drain is the worker. Based on whatever command the gate is receiving, the drain smoothly opens or closes the floodgates, perfectly controlling the massive current going out to the motor. Honestly, it's a brilliant division of labor across just 3 little metal legs.
Section 4. Smoothing with a capacitor.
Here's a harsh truth. Physical motors are messy. As they spin, their internal brushes spark and jump, creating what engineers call electrical noise. We're talking jagged spikes and sudden drops in voltage that can bounce backward and seriously confuse or even damage our delicate control circuit. Enter the capacitor, specifically a 10 microfarad 50-volt capacitor. Think of this little component as a high-tech shock absorber. Because a capacitor can quickly store and release electrical energy, we place it right next to the motor. When the motor creates a sudden spike of messy voltage, boom, the capacitor absorbs the blow. And when the voltage drops for a split second, the capacitor releases a little bit of its stored energy to fill in the gap. It filters the noise, stabilizes the voltage, and protects our entire circuit, making sure everything runs beautifully smooth.
Section 5.
the complete circuit.
Before we get into the actual wiring, let's just trace the logical path of the current step by step. This is the entire story of our circuit in 3 simple beats. Step 1, you, the user, turn the dial on the 10K potentiometer. Step 2, that physical turn instantly changes the tiny voltage signal being sent to the gate pin on the IRFZ44N MOSFET. Step 3, the MOSFET reads that new gate voltage and smoothly adjusts the heavy current flowing through its drain pin to the 5V or 12V DC motor. And just like that, your physical motion on a simple dial seamlessly translates into perfectly controlled mechanical speed.
So let's follow the power as it flows through the full setup. Starting at the bottom, the positive red wire from our 5V to 12V DC power supply routes up to the right pin of our 10K potentiometer, but it also travels straight up to connect to the bottom terminal of our motor and the capacitor. Now let's trace the negative black wire. It connects to the left pin of the potentiometer, and crucially, it connects to the rightmost pin of our MOSFET. Yep, that's the source pin we talked about. Now for the control signal. That green wire comes from the middle pin of the potentiometer, which is our dial's output, and goes straight into the leftmost pin of the MOSFET, the gate. Finally, let's look at the middle pin of the MOSFET, the drain. A red wire connects it directly to the top terminals of the motor and the capacitor, which are wired in parallel. As the gate receives a varying signal from the potentiometer, the drain allows a strictly controlled current to flow through the motor and down to the source. And right there, nestled intimately next to the motor, is our 10UF 50V capacitor, standing guard to absorb all that chaotic electrical noise.
The absolutely crucial takeaway here is that understanding is always greater than memorizing. If you just stare at a diagram with wires crossing everywhere, yeah, it feels intimidating. But when you understand the specific roles, the 5V or 12V motor that desperately needs taming, the 10K potentiometer that acts as the brain but lacks the muscle, the IRFZ44N MOSFET that provides that heavy-duty muscle based on the brain's commands, and the 10UF capacitor acting as the shock absorber, that complex diagram completely transforms. It ceases to be just a jumble of lines and becomes a logical, highly readable story of problem solving.
To wrap up this explainer, I really want to leave you with a thought to chew on. We've just mastered a fundamental building block of electronics. We tamed a DC motor using an electronic valve. But listen, this isn't just about hobby motors on a workbench. Think about it for a second. What other devices in your home rely on this exact same principle to function? From the dimmer switches on your dining room lights, to the variable speed fan in your HVAC system, to the precise motor controls inside your washing machine or your electric drill. This exact concept of using a small signal to control a massive flow of power scales up to run the modern world around you. Thank you so much for joining me on this explainer. Keep questioning how things work, and I'll catch you next time.